Hello and welcome to Easy Projects. So in this video we will make a BCD to 7-segment decoder which can take our binary counter, which we see here, counting on the LEDs, and make that into decimal numbers that can count up on the 7-segment displays. It's very easy to make this decoder, so we'll take the opportunity to look at a few different ways of doing it, a few different types of signal assignments. So let's get started. So I have opened the top level file in the Big Clock project, and it is exactly as we left it last time. We created our prescaler to divide the clock down to 1 second, and then we created our 60-second counter. We now want to convert this into something that's compatible with the 7-segment displays. So the output of this counter will give us a single vector going from 0 to 60. But of course we need to show from 0 to 9 on the first display, and then we need to show from 0 to 5 on the next display to show our 60 seconds. We could of course make up some logic to extract those values out of this output. But it will be much easier for us to make a counter that counts to 10, then followed by a counter that counts to 6. So every time 10 seconds have elapsed, we will increment the next counter. It will of course give us the same result, but it will also give us the outputs in the format that we need to put directly into a BCD to 7-segment decoder. So we'll start by doing that. We can just copy this whole thing. And paste it. Then I think I'll rename this to a 1 second counter and a 10-second counter. So by this I mean how often they should be incremented. The first one we need to count to 10, and we should be able to do that with a 4-bit value. This one down here only needs to count to 6, and that we can do with a 3-bit value. Now we of course need to fix some of these signals because the outputs cannot go to the same, and we need to feed the TC to the enable of this one like we did up here. And to feed this TC to this counter we'll just do like we did last time. We'll copy this signal. Then we'll call it TC 1 second to 10-second counter. And then we'll paste that here and on the enable down here. So now that should be fixed. This TC we still don't care about for now, but these outputs we'll need to fix those also. Now we don't want them to go directly to the LEDs on the board anymore. We want to feed them into the BCD to 7-segment decoders once we make that block. So I'll go ahead and make these signals now so we don't forget. So we'll go ahead and make some new signals for that. We can call it count out to BCD. Let's call it 1 second and 10 seconds. Now a binary coded decimal is normally 4 bits because we need to count from 0 to 9. But down here we only use 3 bits because we only ever need to count to 6. It would probably be easier for us just to make this a 4-bit counter and then make this 4 bits as well. And then just ignore that we will never use the last bit. But I think we will leave it this way so we can see how to fix that later. Now of course we need to route the output to these signals that we just created. And I think now we are ready to make the BCD to 7-segment decoder. We'll go ahead and save this file and maybe just check the syntax. And we didn't get any errors, only some warnings because now we're not using any of the outputs anymore. But we'll fix that later. Of course, now our outputs needs to be the output from the BCD to 7-segment decoder. We create a new file, a VHDL file. And I usually cheat and go in here and copy at least the entity and the library and use from one of the other files, so I don't have to write all the stuff again. Then I just rename the entity. We'll call it BCD to 7seg. And we can get rid of these two. So we'll still need an output, but I think we'll call it segment out or seg out. But we'll also need an input. Let's call it BCD in and make it an input. The input, as we talked about earlier, will be a 4-bit, and the output, since it's a 7-segment display, we will need 7 outputs. You may argue that there is indeed 8 segments because we have the dot point usually. But since that is not related to the binary coded decimal in any way, I'll not include it in this decoder. So that should be it. We'll need an architecture. We'll call it arc of that is. Then we'll need the begin and end. So the way we're going to make this decoder in VHDL is actually very simple. If we start with the BCD in being 0, that means we want to see a 0 on the display. We want all the segments to light up on the display except the middle one. And the way we address these segments is by 1 bit each. Usually I keep the A segment the rightmost bit and the G segment the leftmost bit. We'll take a look at the displays in a moment. So we would write seg out should be, and then to write the 0, that would be 0 and then 1s. So only the G segment is off, and that is when BCD in equals 0. And just taking a look at the 7-segment displays, they look something like this. It's a very bad drawing. We have the A segment in the top, then we have the B, C, D, E, F, and G. So as you can see, for the 0, we turn the G off and light up the rest. Now we want to make a 1. It's just the B and the C. The 2 would be the A, B, G, E, and D, and so on. So now you might already have guessed what we're going to do next. We just write else, like we did in the previous video. And then we have to write the output for the 1, which should be like this. When BCD in is equal to 1. Then we go else. And then you just do the same thing for the 2, 3, 4, 5, 6, 7, 8, and 9. And then we're basically done. So I won't do all that in the video. I'll just pause it now and come back when I have filled out the rest. So we made it from 0 all the way to 9. But what if the binary coded decimal says it should be 10 or 11? In theory it could do that because we still have the 4 bits. And in theory we could write up to 15 here. And if that happened, we would of course have a problem. So we want some way of indicating that we had an error. So we can write else. And then just write E for error. And that should be, oops, one too many. It should be like this. And then we can terminate it with a semicolon. So if none of these are true, then it will just take this. There are some 7-segment decoders that can write the letters A through to F also. And that would allow you to write hexadecimal. But we don't have a need for that in our clock, so we will just leave it out and write an E for error if we get above 9. So this is called the conditional signal assignment in VHDL. And we used that in the previous videos, if you watched those also. It's the most versatile one of the signal assignments, but it also takes up the most code. Now that we are always using BCD in as the condition, there is another statement that we can use that doesn't take up as much code as this. Now just to mention it, you don't have to put BCD in, for example, as the condition on each line. You could put a totally different Boolean expression on each line and it will just run through it almost like an if-else-if structure, because it will check if this is true, then it will do that. If not, then it will check the next one, do that, and the next one, and so on. So only one can be true at any one time. And of course it doesn't check this one first and then that one, that one, that one. It just has priority, so this one has the highest priority and then falling, of course. But we'll perhaps take a look at that in another video. The thing I wanted to get to is when you use the same condition, there is an easier way to do it, and it's called the selected signal assignment. So it goes like this. You write with, and then the input BCD in, select, and then the output. Then we make our assignment arrow and go to a new line. Then we write what we want the output to be, and in this case it's 0, and that is when. And now we don't write the input signal here because we already specified it, that we wanted to use this signal to select what this signal should be. So we write it here as 0. And then we make a comma and go to the next line. And then we just do this same thing for the rest of the conditions. And I'll just fill them in and then come back. And once again, we filled in the signals from 0 to 9. And then if we get above 9, we want to see our error message, our E. So we put that here and we type when others. So now these two things will do exactly the same. You can see up here in the conditional signal assignment, we can specify a different condition for each line, where down here it's all related to the signal we type up here. So that's the selected signal assignment for you. We'll go ahead and use this one just because we can, and we used this one in the previous videos. And we can of course only assign something to the same signal once, so we can't have both. So this is actually it. It's the completed decoder, and now we just have to test if it works. So we'll make sure to save the file, and we'll just call it the same as the entity name. So BCD to 7 sig. Like that. Now we go back to the top level file and we have to instantiate these BCD to 7 segment decoders. And we just do that down here. We can call it BCD to 7 seg and then just the 1s colon entity work dot BCD to 7 seg. Then we do our port map. We had the BCD in, and that we want to connect to this signal up here. And we had our segment out, which we can connect to our output, but we didn't make that output signal yet, so we'll have to do that. I'll just leave it blank for now because we need to make another one of these. We'll call this 10 second here, and we call this signal 10 second. So before we forget, we'll go ahead and make these output signals. We do that up here in the entity. We already have one output, but I think we'll rename that to, let's call it display. And we'll make the first one display 0. And it should be 7 bits, of course, because we have the 7 segments. And then we want to make a new signal and call that display 1. I'll just rename this one. So I'm okay with putting these in here directly, of course, because an output for a 7 segment display will never change. It will always be 7 segments. And the output from this will never change because they are meant to connect to each other. So it's only variable outputs like this that you can change just by putting a new number here. I like to route these to local signals so we can change them if we want. Anyway, let's check the syntax now that we instantiated these two and see if I forgot something. And yes, of course, I forgot to delete the old output. So we can just get rid of this. And now this count out to output, we shouldn't need that anymore. You can see it's not used down here, so we'll just get rid of that also. So that was my mistake. Now it should work. And no, I forgot that we only made this signal 3 bits because we wanted to fix that problem later, and I forgot about that. So we need to do something about this signal because the length of this output does not match this. Because this input expects a 4-bit value and this one is only 3 bits, as we mentioned earlier. So there's 2 ways we could fix this, and it would be easiest just to change this to a 4-bit counter, and then we're just wasting 1 flip-flop. And that's probably also the way I would have done it, because it makes it look a bit cleaner than what I'm going to show you now. The other way to solve it is to split the signal up. So instead of having count out to BCD 10s, we make yet another signal and we call this just BCD 10 second, and we call this just output 10 seconds. Now this one is a 3-bit, that's correct, but this one down here should be a 4-bit. And now down here we want this signal to connect to this signal, but only bit 2 down to 0. But then we also need to say that the last bit of this signal should always be connected to 0, like that. You probably don't have to do this last step since we initialized them to 0, but it will not harm to do that. Then you make sure that it always works. Then we of course need to put the correct terms down here. So this one should be the BCD 10 second, and the output up here should be count out 10 seconds. You can see by doing this, it makes it a lot harder to read than just to say, damn it, we use a 4-bit counter, even though we only need 3 bits. But again, when we're only talking about a single bit, I would prefer to make this 4 bits and then leave this as it was when we started, so that we didn't need these 2 lines and to create 2 different signals up here. But anyway, it should compile now. I know I said that before, but and yes. So 0 errors, 0 warnings. That doesn't make sense. Oh yeah, okay, it's only the synthesis, yeah, because we didn't run the place and route yet, because we of course still need to assign these new outputs to the 7-segment displays on the board before anything will work. And we'll of course do that as we did in the previous videos. We'll go to the pin planner. You can see we got some new outputs here, the display 0 and the display 1. Then it tells us that there are some unknown signals which we can delete. It's our previous output to the LEDs. And these locations, I'll go to the pin assignment table that I showed you before, and I'll get the pins for the segments of the 7-segment displays. So I just put our pins in here, and I think we're ready to go and upload it to the board. And we are uploading, and something doesn't look quite right. Oh, actually, do you see what the problem is? And that's it, the time is up. The signal seems to be inverted, so whenever we send a 1, it's actually inverted to a 0. You can see the 8 was totally off there. That should be a 2, 3, 4, 5, 6, 7, 8 was there, 9, and so on. So we'll have to invert all these signals. Okay, so we make yet another signal. And we call it seg out to display 0. And it should be 7 bits, of course, because we want to use it for the outputs. And we make another one for display 1. Now instead of routing them directly to the outputs, we route them to these new signals. And as we always do, it's display 0 is connected to not this signal, and exactly the same for display 1. Like that. And it compiled, so we'll try and upload it to the board and see if that shouldn't have fixed the problem. And it looks like it did. We just have to check that all the numbers are correct. And it seems like it. So to test if we get an E here, I'll just go ahead and introduce an error. I'll make the first counter count to 10, so that it will try to write 10 in the first display before it counts to 1 on the next one. So there'll be 11 seconds from 0 to 10. And here we go. We are trying to count to 10 on the first display this time. And you can see we get the E. So that's working. Now I'll put it back so it actually counts the correct amount of seconds. So I guess that's it for this video. We took the binary counter that we got on the LEDs here and we transferred it into a decimal number that we can read on the 7-segment display. As you saw, it was not very difficult and it was a quick video. In the next one we'll take a look at the simulation tools and how we can see if it's going to work without uploading it to the board. As I mentioned earlier, it's easy to see if we get 60 seconds in a minute, but it's not very easy to see if we get 50 million clock cycles in a second or only 49.999999 clock cycles. That's where we use the simulation, because we can see the individual clock cycles on the computer, which there's no way we would be able to just by looking at the LEDs. So that will come in the next video, and it will probably be a bit longer than this one. Anyway, as always, if you liked the video, please give it the thumbs up on YouTube. And thanks for watching this video. See ya!